first paper implementing Crystal-Dilithium on FRDM-K64. And we have, I think the presenter is Perez. So first author, please share your screen with us.
Thank you very much. Is it already?
Yes, thank you.
Thank you very much. Thank you. This talk is a joint work with Denisse Ortega. We're from Mexico. And the title is Implementing Crystal-Dilithium on the FRDM-K64. Crystal-Dilithium is a digital signature scheme, and the FRDM-K64 is an NXT board that we use it for this research. So, well, as I said, it's a signature scheme, but it's a lattice-based signature scheme, and is one of the third round candidates on the list quest for finding quantum safe cryptography algorithms. In particular, there's specific sector for digital signatures, and this called for the contest. This is not an algorithm. This is already researched by some more people, and the deal here is trying to implement it on software, hardware, and of course, in this case, in embedded devices, in order to see is it suitable for worldwide deployment in the short future. The other candidate is called Falcon, and this contest is now stalled between these two guys, Dilithium and Falcon. So we chose Dilithium because it has a wider support from the community. The only problem with this quantum safe cryptography standardization is that initially they didn't think about embedded devices per se. So, well, nowadays embedded devices, as you may know, they're a lot of computing power, a lot of memory, a lot of capabilities, and I'm guessing they were expecting these embedded devices were suitable for these much more complex graphic primitives. So the thing is that, well, we can, as we see in the conclusion, well, we can implement lithium in these devices, but it's a bit expensive in several ways. So, as you may see in the paper as well here in the presentation, this is the general schemes. We have, as any digital signature scheme, we have a generation part where key hand, where we generate the keys depending on the security level. Decided we have some parameters to take into account. The thing is that in this case, this cryptographic primitive, it has some heuristic approach for finding the correct parameters. So the authors, the original authors of the scheme, those other, well, they have chosen different parameters. So essentially, there's a lattice, there's a matrix with random vectors, and we do some vector multiplication, and what we want to try to find, or we have to find in this case, for the secret key, is precisely these random vectors, S1 and S2. After the multiplication with the matrix, well, this is a vector multiplication matrix, but it's also discrete. So this we have the modular residue of the operations. So it's impossible, or almost impossible, or computationally infeasible to recover the original vectors. And so we have this as a secret key, and we have the public key just as like that. For the signature part, well, we have make some operations with this matrix. Essentially, we take the high parts and the low parts of some vectors, and that will be the signature. For the verification, well, the thing is that the verification only has to say if it passed or not, and that's what we're taking. We just take the part and with some obviously some algebraic stuff here that we have to do some elimination, and afterwards, well, we have can compare if the digital signature okay for the corresponding value. So we have a file and the signature. We usually have it appended. If the signature appended signature equals to what we have, then we have an unaltered document on hand. This, of course, has to be transmitted over the network or over whatever medium we have. And that's a problem because both the secret key and the public key are much more larger than contemporary cryptography. And also the operations, well, they are simple, but they are much more expensive than what we are used to in cryptography. So that's the deal with an embedded device. So the parameters here, well, we have the K and L from the matrix, the eta and beta and W, which are used in the signature part. And here we have some three security levels for the NIST, 2, 3, and 5. Well, this obviously is number 4, but currently level number 3 is the one that will be probably more used for one. The thing is that these keys are in the order of the 1000 bits, 1900 and 3200 for the signature. So it has some computational, our drainage for transmission because it's actually a package that is quite large. It's more than 1.5 kilobytes, which are used in the regular TCP. So it would be a burden for sending this part. Anyway, if we send a document on the internet or any other medium, well, of course, we'll have to pay for the transmission. For the signature, it's on the order of 3,000. Nevertheless, this is one of the smallest digital signatures which are quantum safe. So, well, that's the best we have so far now. Now, our goal for this approach was that there's another implementation already in embedded devices from Denisse et al. And we aim to get at least 10% of improvement. And we wanted to try different values. Actually, there's some other implementation from the original authors of the lithium. We mix up the parameters, and of course, we also do some software engineering improvements on this curve. We actually are using the Freedom K64 because, well, but there's two reasons. We have available that card here in our current geographic position. There's a laboratory here in town, and well, they also use Cortex M4, which is one of the chosen embedded cards for the next competition because well, it's one of the most available worldwide. So we actually tried these parameters actually for the level 3. Those are the ones we wanted to try in this work. So the reference work from Denisse et al. They use it on Cortex M4. Well, they're using an STM card, and they downgraded the speed of the CPU processor to 24 megahertz. This was to match the flash card on the memory. So they wanted to match it to avoid the memory wall. We didn't work with the 24 megahertz. We used the Freedom NXP with a 120 megahertz. However, the flash card, the memory it's on 24 megahertz also. So anyway, we measure the CPU cycles and no seconds. So what we have here is the speed in CPU cycles from the outers. In the case of the key hand, it's less than 2800 CPU cycles for the key generation, about the same. The Denisse et al. They got very good improvement on 6,000 versus 7,000 over the reference implementation, and for the verification is 2,700 cycles. Well, this is still a lot, but that's what we have. So with our results, well, we use the hardware random number generator from the card. We have, well, as I say, we use 120 megahertz, but the flash card is, I didn't write it down here, but it's on 24 megahertz. We use the MCU Expresso, which is basically just a spin-off of the Eclipse IDE. But anyway, just a random fact. And we use this site P counted for measuring the speed of implementation. Well, of course, we changed some for loops and for loop unrolling and we changed parameters and some minor reorganization of the code in order to have a better pipelining because this embedded device has some super pipelining in the hardware. So we get that we got better results. So in comparison, for the key generation, well, we are about the same. 300, well, 3600. For the sign-in part, we got about the same, and the verification we got about the same, but in our card is without any implementation, but minimal optimization. I mean, for the rest, well, we have only 0.3 optimization for the key generation. However, for the signature, we got about 18% of optimization with respect to the reference implementation, but only the minor difference here. On the other hand, we did have a larger optimization with the smaller security levels. There's one missing table here. It's on the next slide. Oh, I think I missed one slide. Well, there's a verification table here missing, but we got about the same results on this case. Well, nevertheless, the lithium is a resonance game, so that is frequency. We're still working on better ways to improve the code for our board. And well, we also would like to implement it in our board on a different boards. The thing is that, well, this lithium is suitable for embedded devices, as opposed what this says, because with our measurements, we will have feasible speed. The problem here for the embedded devices is for the public key, which we try to reduce, and we will be hoping to reduce further, maintaining the same security level, and which may make it better for energy saving. So, well, that's it. Some time for questions, I guess.
Thank you for the presentation, Mr. Perez. Is there any questions for Mr. Perez? Is there any questions? So I have a question if nobody has any questions. Now, Cortex M4 is, as I understood, is not practical, right?
It's expensive.
In small, devices because it requires a lot of computational power, I guess.
Yes, the Cortex M4 is a large embedded device. Actually, it's 120 megahertz, but it's one of the largest in the line for our ARM devices. There's another one, the M3, which is slightly smaller and we have less capabilities. But yes, the problem is that this is expensive. But we're talking, well, for the pandemics, it should be around $100, maybe 50 if before the pandemics. And usually you have these one is embedded devices, which are only about between $5 to $10. So in comparison, this is expensive one. But Denisse wanted to use the Cortex M4 because this has a larger capability. Now, this Taiwanese, the ESP, for example, they are quite powerful. Actually, they have 7 deep super pipelining, which is impressive for the cost and the size, but they also are about on the same speed. There are other M4 which are larger. I mean the Cortex and the ARM is about 1 gigahertz and even 3 gigahertz in the cell phones. Because I would say it is barely in the embedded world. I mean, it's pushing ahead.
And in terms of security, how did you compare their performance in terms of security? Which one is better?
What do you mean in the M4 versus other cards, or the one that mentioned? Well, the thing is that the Cortex M4 has some cryptographic, hardware-based cryptography algorithms inside the silicon. But the thing is that they're slightly a bit behind. But if we compare with the ESP, which is a way older model, I mean, well, they're ahead because in the case of ESP, they still have on this in the embedded in the hardware some obsolete and already weak primitives. So in that sense, the Cortex-M4 is better because it doesn't have as many as insecure primitives in hardware, but this still have some insecure primitives on hardware that we should not use.
Thank you. Is there any questions for Mr. Perez before we end the first presentation? Okay, thank you so much, Mr. Perez, and we will move to the next paper.